Good morning everyone. I am Anikshan and today I am going to explain red-black trees, which is a very special type of self-balancing binary search tree. The title of my presentation is Red-Black Trees, Balancing the Binary Search Jungle. Red-black trees are an elegant solution that helps us maintain efficient search, insertion and deletion, operation in dynamic data structure. They are widely used in operating systems, programming libraries and database because they keep the trees balanced automatically. Now why the balance matters? Before understanding red-black trees, we first need to understand why balancing is important. Let us consider the problem. If we insert numbers 1 to 10,000 in sorted orders into a normally binary search tree, the trees become like a long chain. Instead of a balanced tree, it becomes similar to a linked list. In that case, the height of the tree becomes n, where n is the number of nodes. Because of this, searching may require checking thousands of nodes, which makes the operation very slow. Now, let us see the solution. If the tree is balanced, then the height becomes log n. For example, instead of checking 10,000 nodes, we might only need around 14 or 15 steps to find a value. That is a huge improvement in performance. Red-black trees maintain this balance using special coloring rules and rotation. This ensures that the tree always performs efficiently regardless of the insertion order. 5 rules of red-black trees. Red-black trees follow 5 important rules that keep the tree balanced. These rules convert a normal binary search tree into a self-balancing data structure. Let us go through one by one. Rule 1. Color property. Every node in the tree must be either red or black. This color property is the main idea that helps control the balance. Rule 2. Root rule. The root node must always be black. This rule stabilizes the tree from the top. Rule 3. Leaf rule. All nil leaves which represent null pointers are considered black. This helps simplify edge cases when performing operation. Rule 4. Red rule. Two red nodes cannot appear consecutively. In other words, a red node cannot have a red parent. This rule prevents the tree from becoming too deep. Rule 5. Black height rule. Every path from a node to its descendant nil nodes must contain the same number of black nodes. This ensures that the tree remains balanced. These 5 rules are the core principle behind red-black trees. Correct red-black trees. This diagram shows the example of a correctly colored red-black tree. The tree satisfies all 5 red-black rules. The black height of the tree is 3. This means every path from the root to a nil leaf contains exactly 3 black nodes. You can also notice that no two red nodes are next to each other. Red nodes are placed strategically in the tree. Usually around half of the nodes are red. This helps maintain balancing while reducing the number of expensive rotation required. Height guarantee. One of the biggest advantages of red-black tree is the guarantee on the height of the tree. There is an important theorem which states a red-black tree with n nodes has height h less than equal to 2 log 2 n plus 1. Let us understand the idea behind this. First, imagine collapsing each red node into its black parent because red nodes cannot be consecutive. This creates a structure similar to a 2-4 tree. Second, we analyze this 2-4 tree. A 2-4 tree with n keys always has height less than or equal to log to the power base n plus 1. Third, we relate this back to red-black trees. Each level of the 2-4 tree corresponds to at most 2 levels in the red-black tree, so that height becomes at most twice the logarithm. This proves that red-black tree can never become long chains like normal WPS trees. This is what guarantees efficient performance. Insertion process. Insertion in a red-black tree starts the same way as in normally binary search tree. First, we insert the new key according to BST rules. After inserting, the new node is colored red. Coloring it red ensures that the black height property is not immediately violated. However, it may cause a red-red conflict with its parent. To fix this, the red-black tree handles several cases. Case 0, root fix. If the new node becomes the root, we simply color it black. This satisfies the root rule. Case 1, recoloring. If both the parents and the uncle are red, we recolor them to black. Then we color the grandparent red. After that, we move upward and check again. This process is called recolor cascade. Case 2 and case 3 rotation. If the uncle is black, we perform 3 rotation. Case 2 require 2 rotation, case 3 require 1 rotation. This rotation removes the red violation permanently. In total, insertion require at most big O log n recoloring operation and constant rotation. This makes the insertion operation very efficient. Example of insertion. Let us see a simple example. First we insert 10. Since it is the root, it is colored black. Next we insert 20. It becomes the right child and is colored red. Then we insert 30. Now we have a problem because 30 and its parents are both red. This violates the red-black rule. To fix this, we perform a left rotation at node 10. After the rotation, we recolor 20 as black. Now the tree becomes balanced again. This example shows how rotation helps maintain balance while preserving BST order. Deletion. Deletion in red-black tree is more complex than insertion. This is because deleting a black node affects the black height of the tree. First, we perform standard BST deletion. If the deleted node was red, then the tree is still valid. This is because red nodes do not affect black height. However, if a black node is removed, a problem occurs. To represent this problem, we mark the replacement node as double black. This means one extra black node is needed on that part. Then we apply fix-up cases. Case 1. If the sibling is red, we perform a rotation so that sibling becomes black. Case 2. If the sibling is black and both his children are black, we recolor the siblings red. Then the double black problem moves upward. Case 3. If the sibling has at least one red child, we perform rotation and decoloring to remove the extra black. These steps ensure the red-black properties are restored. Deletion also runs in big O log n time. Real-world application. Red-black trees are not just theoretical concepts. They are widely used in real-world systems. For example, in the Linux kernel completely fair scheduler, red-black tree stores runnable processes. This helps the system make scheduling decisions efficiently even with thousands of processes. In C++, standard template library, the containers standard is to map and standard set are implemented using red-black trees. This allows fast insertion and search operation. In Java, the class tree map also uses red-black trees for storing ordered key value pairs. Modern databases like RocksDB and LevelDB also use red-black trees inside their in-memory structures. This implementation ensures predictable and efficient performance in real life. Conclusion. To conclude, red-black trees transform a simple binary search tree into a balanced and efficient data structure. By following the 5 color rules, they ensure the tree never becomes too tall. This guarantees that search, insertion, and deletion operation always run in big O log n time. Understanding red-black trees help us see how theoretical concepts in computer science power real-world systems. I encourage everyone to try implementing a red-black tree from scratch to understand the concept deeply. Thank you.